Hello students, I am Azizi, Professor Electronics. In this session, we will develop a new circuit for our microcontroller, and we are using the microcontroller that is AT89C51. In this session, we will develop the circuit to connect some digital inputs, that is switches, with our microcontroller, and we will connect some LEDs on the ports, and we will write our programs using switches and LEDs. In this session, we will learn some new terminologies related to microcontroller circuits, that is power on reset, pull up resistors, pull down resistors, debouncing circuits. So let's start developing our new circuit for microcontroller, that is AT89C51. For this we'll use the software that is Proteus software, and here in Proteus we'll go for the new project, and here we'll assign the name that is AT89C51 project 2, and we'll write the name that is AT89C51 underscore project 2. So here we have assigned the name to our project, and now we'll select the folder to save our project. Browse. We'll go to the course contents, and here we'll select MCS 51 projects. OK, select the folder, and next. Create a schematic from the selected template. OK, next. Do not create a PCB layout. OK, next. No firmware project. Next. And finish. And here we have the template, and we will develop our new project on this template. First, we'll select the microcontroller. We will go to the parts, and here we will write that is AT89C51. And here we have the microcontroller, that is AT89C51. We'll select the microcontroller. Now we'll select the component, that is push button. So here we will write button. Here we have button, SPST, push button. We'll select the button. Now we'll select the LEDs, and here we will write LED. And here we can find LED red, animated LED model red, and we'll select this LED. And now we'll select some resistors. From 0.6 watt metal film, we will select a 4.7K resistor. Here we have 4.7K resistor. And now we'll select another component, that is ULN2803 Darlington driver. So here we will write ULN2803, and here we have ULN2803, the Darlington driver IC. OK. Rest of the components that are required to complete our circuit we'll select later on. OK. First we'll place the microcontroller, that is AT89C51. Now what are the requirements to configure this device as microcontroller? First of all, we'll connect the external access pin with the 5 volt, because if we'll connect this pin, that is external access, with the ground, this device will work as microprocessor. So first we'll connect it with 5 volt. OK. Here we can observe that VCC and ground pins are not visible. If we'll select the device, right click, properties, and here we'll select hidden pins, and here we can see pin ground is connected with ground, and pin VCC is connected with VCC, that is plus 5 volt. It is understood that these pins are already connected with VCC and ground. Therefore, there is no need to show these pins in schematic. OK. OK. Now what are other requirements? At pin 9 we can find the reset input of the microcontroller. So what is the requirement for reset input? It requires a power on reset circuit. So what circuit is required to reset the microcontroller? This circuit is called power on reset. Because this pin is active high, so we'll develop a circuit which will provide a high pulse whenever we'll power up this device, or whenever we'll power up our circuit. So let's see what is power on reset circuit. Here we can see different types of power on reset circuit. We can develop the power on reset circuit using NAND gate like this. Here we can find a resistor and a capacitor. If we'll power on the circuit, the capacitor will be short circuited and the output of the gate will be high because it is a NAND gate working as inverter, and when the capacitor will be charged, then the output will be low. So we can say that whenever we'll power on our circuit, a high pulse will be available at the output of the circuit, and due to that high pulse, the microcontroller will go to the reset vector, that is 0000H. In our case, that is 89C51 microcontroller. It is not necessary that all microcontrollers should have reset vectors at 00H. For this, we have to go through the datasheet of the particular microcontroller and to find which vector is the reset vector. And here we can find a typical circuit for 89C51 microcontroller power on reset circuit. And here we can see a switch. It is for manual reset. Whenever we'll power on the circuit, this capacitor will be short circuited and the voltages will come across this 8.2K resistor, and a short duration reset pulse will be applied at pin number 9 of 89C51 or 89C52 microcontroller. And whenever we'll press this switch, again the pin number 9 will go high and the microcontroller will jump to the reset address, that is 0000H, because this device has a 16-bit address length. We can find some special power on reset circuits and manual reset circuits for microprocessor based and microcontroller based systems. If the power on reset is active low, as in case of PIC microcontrollers, we'll connect a resistor with VDD and we'll connect the capacitor with the ground, and whenever we'll switch on the circuit, the capacitor will be short circuited and a low level will be applied at reset input. In this case, the microcontroller again will go to the reset vector, and here we can find a manual reset input. Whenever we will press this switch, this pin, that is MCLR, master clear, will be low and the microcontroller will jump to the reset address. But in Proteus, to simulate the microcontroller, there is no need of power on reset circuit. So we'll just connect this pin with the ground, that is pin number 9. We will connect this pin to the ground and we'll select the ground from here and we'll connect this pin with the ground. We will not connect the crystal oscillator with this microcontroller because we have learned that how to connect a crystal oscillator with these pins in our previous circuit. So we'll leave these pins unconnected and we'll select the crystal oscillator frequency from its properties, added properties, and here we can find the crystal oscillator. Clock frequency is 12 MHz. Now we'll connect the LEDs with the microcontroller port, and here we'll connect the port 0 to connect the LEDs with this port, that is from port 0.0 to port 0.7. Now we'll learn that how to calculate a resistor to drive a LED. First we'll connect the Darlington driver, that is ULN2803, with the microcontroller. We'll place the Darlington driver, that is ULN2803, here, and we'll connect it from port 0.0 to port 0.7 like this. Port 0.0, port 0.1, port 0.2, 3, 4, 5, 6 and 7. If we'll go through the datasheet of MCS51 family, we'll find that there are no internal pull-up resistors for port 0 because this port is multiplex port. It can serve as data and address, so the pull-up resistors are not there. And if we want to use this device in microcontroller mode, then we have to connect the external pull-up resistors with this port. So we'll connect 8 4.7K resistors as pull-up resistors with this port. Resistor 1, 2, here we have placed 8 4.7K resistors. Now we'll connect these resistors with the port. So we'll connect the resistor like this with port 0.0, port 0.1. Here we have connected 8 resistors with port 0 of the microcontroller, and the other end of these resistors will be connected to the VCC. So we'll connect the second end of all these resistors with the 5 volt. And now we'll connect this end with the 5 volt. Drag the object like this and we'll connect this end with the 5 volt. Now we'll connect 8 LEDs with ULN2803 Darlington driver. This Darlington driver IC has 8 transistors in it. All outputs are open collector and can drive the load up to 500 mA, that is 0.5 ampere. So we'll connect the LEDs with the output, that is from collector 1 to collector 8, and here we have the common pin, pin number 10, This pin, that is pin number 10, is the common point for all 8 freewheeling diodes installed in this ULN2803 Darlington driver. Freewheeling diodes are installed in this device to drive relays and inductive loads. Here we can find from the datasheet of ULN2803 IC. It is octal high voltage, high current Darlington transistor array. And here we can see the equivalent circuit for single stage, that is 1/8 ULN2803 driver. Here we can find the 2.7K resistor on the base of first transistor stage, and we can find a diode which is called freewheeling diode, and it is used to drive the inductive loads like relays and solenoids. Because LEDs are not inductive load, so there is no need to use these freewheeling diodes. But if we will not connect this pin, that is pin number 10, the common pin for all 8 internal freewheeling diodes, then this IC will not be able to simulate its function. So we will connect this pin with the 5 volt. Now we will connect 8 LEDs with this driver, that is ULN2803. We will connect the first LED here, LED 2. Here we have placed 8 LEDs on our schematic. Now we will connect the cathodes of these LEDs with ULN2803 Darlington driver. This Darlington driver IC has no VCC input, but it has a common ground which is internally connected with the ground. So there is no need to show the ground in schematic. Now we will use the 8 resistors to limit the current of these LEDs, and we will learn that how to calculate the current limiting resistor values. To calculate the current limiting resistor for a LED, we require 2 parameters, that is the forward voltage for the LED and the forward current. Here we can find the forward voltages are 2 volts for this particular red LED, and the rated forward current is 20 milliampere, which is necessary to go through the data sheet to calculate any parameter related to the device. And here we have seen 2 parameters, that is forward voltage and forward current. Forward voltages are 2 volt and forward current is 20 milliampere. Now we will calculate the current limiting resistor for this LED. As we have seen 2 parameters for the LED, that is forward voltage and forward current. And here we have the symbol for a LED. It has forward voltage, that is V forward equals to 2 volts, and I forward is 20 milliampere. And if you would like to drive this LED on 5 volt, then we can calculate the current limiting resistor like this. We will connect the VCC, that is plus 5 volt here, and we will use a current limiting resistor here, that is R, and we will connect the cathode with ground. Now we will calculate the resistor like this. The value of the resistor will be R equals to the VCC, that is 5 volt, or we can drive this LED with 12 volt, but here we are using 5 volt, so we will use the 5 volts. So here we will write 5 volts minus the forward drop, that is 2 volt, divided by the current of the LED, that is 20 milliampere. It means 0.15 into 10 raised to the power 3 and 150 ohm. So we will use the resistor of 150 ohm as current limiting resistor for this LED. Now what will be the wattages for this resistor? So we can calculate the wattages for this resistor like this, because W, that is watt, is equals to I into V, and the voltage across this resistor will be 3 volts and current will be 20 milliampere. So we will write 20 milliampere multiply by 3 volts, it means 60 milliwatts. So we can use a standard quarter watt resistor, that is 150 ohm, 0.25 watt resistor as a current limiting resistor for this LED. Now we will go to the components and we will select the resistor of 150 ohm, and here we have 150 ohm resistor. Now we will connect 150 ohm resistor with each LED. So here we will place the resistor, rotate clockwise, and now we will copy this resistor from here. And we'll connect the next end of all these resistors with 5 volt. Just double click here, and the last section will be repeated. And here we have completed the LED circuit, and now we'll interface 3 switches at port 2 of this microcontroller. We'll select the button, and here we will place 3 switches, switch 1, switch 2 and switch 3, and we'll connect these switches from port 2.0, 2.1 and 2.2. We can increase the switches as per requirement of our project, and we'll connect the next end of these switches with the ground, or we can also connect these ends with the VCC. If we'll connect these end of the switches with the ground, then the next end which is connected to the port will be connected to a resistor, which will be connected with a 5 volt, and we'll call these resistors as pull-up resistors. So let's see what are pull-up and pull-down resistors. We can interface the switches with the microcontroller as input in 2 ways. The first is called active low and second is called active high. Say for example, we have input of our microcontroller like this, say port 2.0. We can connect a switch with this port like this. Here we have a switch. We can connect this switch with the port 2.0. Now we can make this input as active low or active high. If we want to configure this input as active low, then we'll connect the next end of the switch with the ground like this, and we'll connect a resistor with the 5 volt and connect the next end of this resistor with port 2.0, and here we'll use plus 5 volt, and the value of the pull-up resistor will be 4.7K. And if the state of the switch is unpressed, then here we have plus 5 volts because we have used a pull-up resistor with this port. But if we'll press this switch, then the port, that is port 2.0, will be low. Similarly, we can connect a switch with the port in a second way like this. Say for example, we have port 2.0 here, and we'll connect the switch like this. If you want to make it active high, then we'll connect the next end of the switch with the 5 volt like this, and we'll connect port 2.0 with the ground using a pull down resistor, and the value of the pull down resistor will be 4.7K. In this case, we can say that the input is active high, because if the switch is not pressed, then the voltages at port 2.0 will be 0, and if we'll press the switch, then 5 volts will be there at port 2.0, and we'll say that this input is active high. So here we have learned that the concept of active low and active high, and it is better to discuss the concept of debouncing circuit here because we are using switches. So if we'll press a switch, we will not have the clean output of the switch. Say for example, if we'll press this switch, and if it is connected to 5 volt and next end is connected with the ground using a 4.7K resistor, and here we have the output. If we'll press the switch, it will bounce many times like this, and it will go high. And if we'll release this switch, again it will bounce many times and it will go low. To filter out this high frequency, we can use hardware or software techniques to eliminate this high frequency from the input. Here we have high frequency, and this frequency is called bouncing, and we can use 2 techniques, that is hardware debouncing technique and software debouncing techniques. So let's see what are debouncing circuits. Here we can find debouncing circuits. Here we have connected a switch, and we have a resistor, that is 10K, connected with the 5 volt, and here we have 100 ohm resistor. If we'll press this switch, it will produce bouncing like this. So here we have used a capacitor to filter this high frequency, and here we are using a Schmitt trigger IC to make it TTL compatible, and here we'll have the clean output, that is the rising edge and the falling edge which will be compatible with the TTL family, and we can calculate the switch open time and switch close time. Here we can see whenever the switch will be pressed in active low system, then the switch will bounce many times, and whenever we will release the switch, again it will bounce many times. And our requirement is a clean rising and falling edge. To eliminate this high frequency, we can use hardware debouncing circuits, but we can also eliminate this high frequency in software using software techniques. Here in our circuit, we will connect the next end of these switches with the ground. Like this. And now we'll use three 4.7K resistors as pull-up resistors, and we'll connect the one end of the resistor with the port, that is port 2.0, 2.1 and 2.2, like this. And next end of the switches will be connected with the 5 volt. Here we have completed our schematic diagram for the microcontroller by connecting 8 LEDs and 3 switches. Thanks for watching the assembly language programming course. We hope that you find this course very helpful to learn assembly language programming. If you feel that this course contributes and enhances your embedded system design knowledge, then go ahead and hit like, share and subscribe buttons, and do not forget to press bell icon to stay updated with every new upcoming video from Electroeducators as soon as it goes up. Electroeducators also offers technical consultancy in following fields. For assistance regarding technical problems, projects and any consultancy, feel free to reach out at our email address electroeducators@gmail.com. Okay, see you in next lecture.